Okay, as a little warm up here, I want to actually relate what we just looked at with our product and quotient rules to finding derivatives of other trig functions, and then we'll kind of build off of this as we go. But it's important for you to see the derivation of these because, for one thing, it's easy to forget some of these. There's a lot to memorize here in AP Calculus, and the more you understand where things come from, the easier it is to make up for those times when you forget something. Okay? So, you can re-derive things. And we're going to do that here with tangent by deriving what the derivative of tangent is. If you look at the bottom of the screen, we already can see it's supposed to be secant squared. But how do we come up with that? Well, let's take a look at this and use a little bit of our trig from last year as we develop this, okay? So, before I try to take the derivative of tangent, I'm going to first of all think about how could I rewrite tangent? Yeah, it's sine over cosine. Now, the reason why it's significant to do this is because we already know the derivative of sine and the derivative of cosine. Okay, so when I go to find my derivative for tangent, I'm going to use the quotient rule. Okay, so.
I thought you were going to do the one for sine. Oh, and you are.
Okay, so we have low D high, so cosine x times, what's the derivative of sine? Cosine. Minus high D low, what's the derivative of cosine? Negative sine. Okay, all over low squared, so cosine squared x. Alright? So, we see here that in the numerator we have a cosine squared x plus a sine squared x, because we have a double negative, all over cosine squared. And what's sine squared plus cosine squared equal? 1. Alright, so we have now a 1 over cosine squared, and 1 over cosine equals secant. So 1 over cosine squared is secant squared x. Okay? So we just derived the derivative of tangent using sine and cosine. And the fact of the matter is, we could actually do this with any one of our other trig functions. We have the cotangent, which is cosine over sine. We have the cosecant, which is 1 over the sine. And we have the secant, which is 1 over the cosine. So in each of those cases, we could actually find the derivative using the quotient rule. Okay? Now, here are a couple more rules that we need to make sure that we memorize. And we could derive all of these. I'm not going to derive all of them. But let's go ahead and just derive one of them. Let's say we do cosecant, okay? So cosecant, we're going to do by taking the derivative of cosecant. Of cosecant. And you're right, it's the derivative with respect to x of 1 over sine of x. So let's use our quotient rule. Okay? It's low d high. What's the derivative of the numerator? 0. Okay? Minus high d low. What's the derivative of the sine?
Cosine.
26.
low D high. Shouldn't you say low high D because it's the derivative?
If that helps, it just rolls off the tongue a little bit. Like saying dy dx, it's d high. Okay. Now this is over the denominator squared. Okay? So of course sine times 0 is 0, and we have a negative cosine x over sine squared x. And I'm actually going to rewrite this a little bit. I'm going to rewrite this as a negative cosine x over sine x times a 1 over a sine x. Okay, I'm just splitting up the sine squared. And because I'm making this multiplication, I'm allowed to do this. And of course, what is cosine over sine? That's cotangent. And 1 over sine is cosecant. Okay? So we have a negative cotangent times cosecant, or cosecant times cotangent.
Do you think we might have time in the test to derive everything?
No. You're going to need to memorize them the best you can. If you happen to forget one of them and you have to rederive it, you'll probably have time for that, but you're not going to have time to rederive everything. So, now, let's look at some patterns here with the derivatives, and I'm actually going to go ahead and list the ones that we already knew as well. The derivative with respect to x of sine of x is cosine of x, and the derivative with respect to x of cosine of x is a negative sine of x. Okay. Now, you'll notice, what do you notice about the derivatives, or what patterns do you happen to notice here? Any patterns?
Yeah, what kind of related to tangent?
Patterns?
Yeah. Not really with the e to x, that's a totally different one, but
Well, to line.
Well, all the co's are negative in a derivative.
okay, if you're taking the derivative of something that starts with cotangent, cosecant, cosine, they all end up negative. That's an easy, one of the most common mistakes students make is to put the negative on the wrong ones. Okay, so if you're taking the derivative of something that starts with the derivative will be negative. Good. Okay. Notice you remember your Pythagorean identities? Sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. 1 plus cotangent squared equals cosecant squared. The things that went together there go together here. Tangent and secant go together. Cosecant and cotangent go together. Alright? So there's another connection there that'll help you remember which ones go together. The tangent and cotangent end up being something squared, whereas the secant and cosecant end up being a product of two different trig functions. Okay, that's another kind of connection that you can make that might make this easier for you to remember. Okay? So just a little something that hopefully will help. Okay? So let's, and then the derivative of e to the x, we throw this one in here just because it's helpful to know, the sooner the better. And it's super easy. The derivative of an exponential e to the x is just e to the x. Okay? That's easy. All right. So let's run through a few examples here. The derivative of x minus the tangent of x. Okay, so we're finding dy dx. Do we have to use any special rules to take the derivative of this one?
Yeah.
Like the product rule or quotient rule?
No.
No, or power rule?
No.
No, this one's just the ones we have memorized. So the derivative of x is
0.
1.
One.
Sec square x.
Very good. 1 minus the secant squared x. Very good. Okay. If you want to keep going, do you guys know what 1 minus secant squared would equal?
Yeah.
So secant squared.
No.
Tangent square.
Tangent
No.
squared?
Negative tangent squared.
Of course.
What's
Okay. Remember, it's 1 plus tangent squared equals secant squared. So if you subtracted the secant squared over to that side, you'd have to subtract the tangent squared over the other side. Okay?
I'll
So
have to
next,
review.
will you give us a table which has identities on them?
Nope.
Oh my god.
In AP, they don't give you anything.
But in previous on they give us the whole thing now, we don't need to remember anything. We just need to remember.
Well, for your final exam, you got
Yes.
that. But that was just us being really nice.
What about the AP test?
They're not really nice to you. They don't give you anything.
AP test, we'll just spend the first half hour deriving everything.
So,
But then
No.
after that,
honestly though, by the time we're done with these, memorizing these really should not be an issue. You're gonna use them so many times that if you're really focusing and you're really, working through these and thinking, you'll have them memorized in no time.
You're gonna be so
Just
much,
by using them so much.
so
okay.
much harder stuff like this can be easy.
This'll seem easy, yeah. Alright. So now, y equals x times the secant of x. If I'm gonna find the derivative,
Secant x, tan x.
okay, that's the derivative of secant
Was cool.
Oh.
is secant tangent, secant x times tangent x. How do we find it though if it's x times the secant of x? Product rule, okay? So, it's gonna be, if you remember, you need both of them twice added together, but one time you take the derivative of one of them, the other time you take the derivative of the other one. So, secant times the derivative of x,
One.
that's just 1, plus x times the derivative of secant.
X, tan x.
Yeah, there you go. Okay? And you can just leave it like that. Okay?
Do you have to
I'm sorry, what?
Do you have to factor?
If you really want to, you could take out a secant x and make that a 1 plus x times tangent of x. That might be useful if, for example, you were finding where the derivative equaled 0 or something like that. But okay, let's try another one here. We want to differentiate the both sides of y equals 1 minus cosine x over sine x equals cosecant x minus cotangent x, and then show that they are the same. Okay, so there's a little bit of identity work here.
These are the ones where you give us the final answer, then we have to go backwards and get it.
Yeah, we did identities, proving identities. Here, this is a little different. We're going to prove that these two have the same derivative. Okay? So, let's start with the right side since that's the easier one. It's just subtraction. What's the derivative of cosecant?
Negative cosecant cotangent.
Negative cosecant cotangent. Okay. And the derivative of cotangent?
Negative cosecant squared.
Okay, so it's minus a negative cosecant squared. Okay? Now I'm gonna wait on this one. I'm gonna wait to simplify anything until I get the other one, and we're gonna have to try to make these look the same. Okay? Yeah, Davi?
Wouldn't negative cosecant squared be positive? So this minus with this bottom.
Yeah, it's minus a positive.
So why did you put plus cosecant squared?
Oh, it's not negative cosecant squared.
Oh, okay.
That's not what the rule is. It's negative cosecant squared.
So it will always be.
Yes, yes. Okay. All right, so then we have here 1 minus cosine x over sine x. How are we going to have to find the derivative of this?
Quotient rule.
Quotient rule, there we go. All right, so low d high minus high d low over low squared. So low times the derivative of the top. What's the derivative of our top here?
Negative sine x.
No, sin x.
Sine x.
Oh,
Because it's minus, it would be 0 minus a negative sine x. Go ahead and write it out if it helps, okay? So there's our low d high minus high d low. The derivative of sine is cosine all over sine squared x. Okay? So let's simplify a bit here. We have sine squared minus cosine plus cosine squared. Okay?
How about the one?
all over sine squared x.
How about the one?
We distribute the cosine to both of these, so that's why, and we distribute the negative to both of these, so that's why I got a minus cosine in the middle
Can
there.
you use sine squared x plus cosine squared x is just 1?
Yeah, you can. Okay, so now we've got those. That's just a 1 minus cosine x over sine squared. So now my goal is to make the right and left hand sides here equal to each other. My guess is that simplifying, well, which do you think would be easier to get? To keep going with this or to go to the other one?
Go to the other one.
Alright, let's try the other one. Okay, so let's switch back over here. So this is going to be a negative 1 over sine times, what's cotangent?
Cosine over sine.
Good, cosine over sine. And then cosecant squared is?
1 over sine x.
Good, 1 over sine squared x. Alright. So notice this first one I can write as a negative cosine over sine squared plus a 1 over sine squared. And what do you know? It comes out to 1 minus cosine over sine squared. Okay? Not too bad. So, with example 4 here, the main thing with example 4 is just to make sure that you don't make your life more difficult than it has to be. Okay? So in each of these cases, we actually do not need to use the quotient rule for any of these. Okay? And that is because you can look at these as a constant multiple. Alright? Now, when we looked at limits, we said that if you take the limit as x approaches c of some constant times the function, you could take the constant out, take the limit of the function, and then multiply by that constant at the end. Okay? Well, because derivatives are limits, the same thing applies. If I'm taking the derivative of some constant times a function, I can take the constant out and multiply it by the derivative of that function. Okay? So, in this example here, let me erase all that so that in this example here, we could rewrite this function as 1/6 times x squared plus 3x. Okay? So then, if I'm taking the derivative, I could simply do 1/6 times the derivative of the x squared plus 3x. Now you don't have to write it out like this, but this is how you can process it in your head. Okay? So I'm going to take 1/6 times 2x plus 3, and now I'll distribute the 1/6 in, and I get 1/3 x plus 1/2. And there's the derivative with respect to x. Mhm.
If I factored x squared plus 3x, and were to get the derivative, could I get the derivative of the isolated x and the things inside the parentheses and multiply them together, or would this not work?
Well, that's a good question, but let's think about that. If I took this and made it 1/6 x times x plus 3, what do we have to do when we're multiplying? Can we just take the derivative of the one and the derivative of the other and multiply them together?
I think you can do
What do we have to use when we have multiplication?
Product rule.
Product rule.
it.
Okay? Notice the difference here is the difference between multiplying by a constant 1/6 and multiplying by another function 1/6 x. Okay? So in this case, we wouldn't want to, I mean, you could do that, but you would have to use the product rule, which makes it more complex. Okay? Another example here, if I view this as 5/8 times x to the 4th, okay, then I can simply take the derivative of x to the 4th, which is 4x cubed, and then multiply that by the 5/8. So this would be 5/2 x cubed. Okay? Even in something like the last one here, this last one,
Would that be quotient rule though?
we could do the quotient rule. We could also view this as something else. Watch this. If I pull out the -3/7, notice it's all multiplication, so I can view it as a -3/7 times 3x minus 2x squared all over x. What could I then do in the parentheses?
It would be 3 minus 2x.
I could cut the x's, I could reduce it down, so it's 3 minus 2x. So now it's a -3/7 times 3 minus 2x. There was a common factor of x in the numerator that I could cancel with the denominator. And now, taking the derivative is actually pretty easy. It's dy dx equals a -3/7 times -2. Okay?
How are you able to just split up the 7 and the x like that?
Well, because it's multiplication. You have multiplication,
Oh, okay.
so I pull it out there as a fraction.
Got it.
Okay? Now, Let's look at example 5, okay? Example 5, we want to sketch the graph of a differentiable function. So if it's differentiable, it has to be continuous, such that f is greater than 0 and f prime is less than 0 for all real numbers x. Okay? So, a differentiable function. That means, like we said, it has to be continuous, but f is greater than 0. So what has to be true about this entire graph?
Has to be above the x-axis.
Has to be above the x-axis. Good. Okay? So, that's first part. Above x-axis. However, f prime has to be less than 0. What does that tell us about our
It's negative.
graph? What?
It's negative.
Below it.
Okay, so the derivative is negative, which means our function is
Negative.
decreasing,
Yeah.
right? Decreasing. So it's decreasing. Well, how are we going to be decreasing over the entire function, but still be above the x-axis for the whole function?
Horizontal asymptote.
Yeah, we've got a horizontal asymptote. So watch this. We're going to have something that looks like this. Okay? It's decreasing the whole time, but it never actually goes and hits the x-axis or goes under the x-axis. Okay? So that's the kind of reasoning that you might need to do as you're working through that. Okay? Now, example 6 is another one. Here are the graphs of f, f prime, and f double prime. Which one is which?
F is the parabola,
You've got,
because it's the largest one you would do. F is the parabola, F prime is
The
the
diagonal line.
diagonal, yes.
And F double prime is the straight line.
I
I'm
know
sorry.
this, I know this
F double
because
prime is the,
you reduce the degree when you get the.
okay,
the exponent.
we're reducing the degree. Good. So the highest degree here is the parabola. So that would be the function, right? That would be f. All right, good. So the parabola here is b. Or let's just use the letters. Oh, I can't do it now. So that's f. What's the next lowest degree?
the diagonal line.
The diagonal line, okay, because that still has an x in it. It's something x plus something. So that's our first derivative. And if you take the derivative of a linear function, you get a constant. Okay, a constant, the horizontal line.
Mr. Hickson, which, oh, is this, lesson 17?
Yes.
Oh,
All right, now we're going to skip number 7 for right now. Okay? We're going to skip number 7 for right now. This is getting into using our calculators to do a quadratic regression. We'll come back to this sometime in the future. Okay? Or in fact, you know what I'll do? I'll record this one. And you guys can kind of watch this on your own, and that way you can stop and go back. You can take the time you need to get it into your calculator just right. But I'll record this one and insert it in here so that you guys can see the whole thing. Okay, so number 7 here, it says the table shows the number of motorhomes N in thousands in the United States and the retail value V in millions of dollars of these motorhomes for the years 1992 through 1997. The year is represented by T, with T equaling 2 corresponding to 1992. In other words, they just made 1990 0. Okay, so 1990 is our starting point. So we have 2, well, I'll just circle it. 2, 3, 4, 5, 6, and 7. Those are our values of T. Okay? Now remember, N is in thousands. And V is in millions of dollars. Okay? Now, this first part can be a little bit challenging. Use a graphing utility to find quadratic models for the number of motorhomes, N of T, and the total retail value, V of T, of the motorhomes. Okay? Now, let's look at the calculator and see what this represents. The first thing that you need to do is go to Stat and hit Edit. And we're going to put the times in list 1, the number of motorhomes in list 2, and the value in list 3. Okay? So go ahead and do that real quick and I'll pause it. Okay, so I'll show you list 3. Again, you're hitting Stat and Edit. Okay, I've already got my times in list 1, my numbers of motorhomes in list 2, and now I need the values in list 3. So 7544, 9897, 9768. And then 9139. Okay? How are we doing on getting our data entered?
But the graph looks like
Okay? Well, we're going to get to the graph here in a second because it says find a quadratic model. Okay? Now, just to remind ourselves here, we did do list 1, list 2, and list 3. Okay? Now, if we're making a quadratic model, we need to use our regression function on the calculator. Okay? Is there anyone still getting the data into their calculator? Okay, so to use the regression to get a quadratic model, we're going to do Stat again, but notice come over here to Calculate, and you've probably used linear regression before, but number 5 has quadratic regression. Okay? Now, the important thing is we want to make sure that we use the appropriate lists. In both cases, list 1 is going to be our independent variable. That's the year. Okay, and we're saying that the number is dependent on that. So this first one we're going to use is list 2. Okay, oh, where'd it go? There we go. All right, so list 1 and list 2. One other thing here, we're going to store the regression equation. We got to store it in one of our y variables. So here I go to vars, right here above tangent button, variables, y variables. This is a function, and we're going to do y1. Okay? Now, you know the y equals where you plug stuff in to graph it. Y1 is the first line there. So this is going to give us a quadratic regression model, and then it's going to put that model in Y1. Okay, so I'm going to hit enter. And notice here, it gives me some different data. And notice the form of the quadratic regression model. It's ax squared plus bx plus c. So our first one here, n of t, is a negative 9.664 x squared plus 90.741 x plus 77.503. Make sure you do 3 decimals all the time for AP. Okay, so I wrote those down. Notice though now if I hit my y equals, there it is right there. Okay? So there's my quadratic model. Now, we may or may not have to graph it, but it's always helpful to just save it there regardless. Okay? Any questions so far? Okay. So, if you have the TI-83, it doesn't give you the nice little menu that asks you for which lists you want. So you have to use down here, list 1. So you hit second list 1, comma, second list 2, comma, and then go into variables and choose your Y1 that way. Yeah, the comma is right above the number 7 there. Okay? I'll show you again doing the second quadratic model. 3 decimal places. Yeah, they don't do sig figs, they do decimal places. So, all right, so one more time I'll show you here. Stat, calculate. We want quadratic regression, number 5. This time though, I'm going to use list 1 and list 3. So I hit second 3 to put list 3 there.
How did you go back to the?
I just hit stat, calculate. So you hit the right arrow, and then number 5 is quadratic regression. And then I'm going to store this regression equation in my Y2. So Y2, and I'll calculate that. And notice here is my model for V of t.
Wait, how did you get L3?
It's above the number 3. If you hit second L3. Okay? So V of t is negative 276.464 x squared plus 2,987.693 x plus 1,809.971. Okay? And that's how we find a quadratic regression model. So now that we have these models, guys, okay, if I have A equals V of t over over n of t, let's think about what this is going to give us.
The retail value will be per multiple.
Okay, yeah, it's going to give you, now, notice our units of measure. It's going to give us our value in millions per 1,000 of mobile homes. Okay? So for every 1,000, it's going to give us, our value for each 1,000 as the year goes up. So it's almost like a unit price. How much would 1,000 unit mobile homes be worth in 1992 or in 1993 or in 1994? Okay? So that's our value in millions of 1,000 mobile homes. Okay? Now, A of t, for sake of time, we're not going to do this, but you'd have to use the quotient rule, okay, to find A prime of t. What would that tell you, though?
Wait, do B already?
Yeah, that's what we just said. It's the value in millions of 1,000 of every 1,000 mobile homes.
Would it give you like the rate at which it's just increasing?
Okay, it's the rate of change, yes, of 1,000 mobile homes, okay, of the value of 1,000 mobile homes. All right, so it's a rate of change. So from year to year, how much is their value changing? That's what that's giving us.
It's like the acceleration. Or is it the like?
It's like velocity, okay? It's a rate of change of the value of those 1,000 mobile homes, okay? So you could use that then, and you could go through and look at, okay, the values were increasing here, and then maybe they were decreasing in this year. So maybe they were more popular at one time and then they were losing popularity, so their values were decreasing. And you could kind of identify, you know, when the ideal time was or the most popular time was or whatever. Okay? So that's it for number 7. Now, this lesson is also about higher order derivatives. We talked about this a little bit when we looked at rectilinear motion, okay? Finding the second derivative of these functions. So the second derivative is what? What are we doing when we're finding that? Yeah, finding the derivative and then finding the derivative of that. So you're taking the derivative twice, all right? Now, the same things still apply. You would want to simplify things first before you take a derivative. Like in this first example, I'm going to rewrite this as by splitting it up into 3 separate parts, all over x. I can reduce the first one down to x squared over x is x, plus 2x over x is just a 2, minus 1 over x, which is x to the negative 1. Okay? I simply split it up into 3 separate parts. Now I'm going to take the derivative of that, and I have a 1 plus 0 minus a negative 1, so now it's plus x to the negative 2 power. Okay? So I just have 1 plus x to the negative 2. Now if I'm taking the second derivative, the derivative of 1 is 0. The derivative of x to the negative 2 is a negative 2x to the negative 3rd. So now I'll simplify, make that negative 2 over x cubed.
Why is it plus x to the negative 2?
Because you already had a minus, and then you had to bring the negative 1 out in front with your power rule. So it was minus a negative 1x to the negative 2. Right here, you had to take this negative 1 out in front.
Oh, so then it moves.
So we had a double negative now.
If you ask us to simplify, get the derivative and simplify, can you let it with a negative exponent? Or do you have
No, you should simplify negative exponents. Okay. All right. Good reminder of our trig functions here. What's the derivative of secant? Secant x times tangent x. Good. So now if I want to take the derivative of that, what am I gonna have to use? The product rule, there we go, okay? So, the second one times the derivative of the first, which we already know is secant x tangent x, plus the first, oh, that's not signed, the first times the derivative of the second. What's the derivative of tangent? Secant squared x. Good. Secant squared x. Alright, so we can then simplify this a little bit. Secant x times tangent squared x plus secant cubed x. With the trig functions, it's always kind of a question of how far do you simplify. You know, you can go any of a number of routes with this. I mean, you could make the tangent squared into a secant squared minus 1, and then everything's in terms of secants. We could have factored out a secant right here. That you just kind of have to read the situation and see what you need and simplify as necessary.
But is this okay, or do you have to go deep?
I'd be fine with if you left it like that, okay? Sometimes what you may be asked to do though is to show that the second derivative equals something else. So,
Oh, equals.
like, show that it equaled a secant squared minus secant plus secant cubed. And in that case, okay, I've got to get that tangent squared to be a secant squared minus 1.
Alright.
Okay? Or I guess, yeah, that would be a 2 secant cubed minus secant. But anyways, now, notice here on example 9, it goes beyond just the second derivative. We can have a third derivative. Okay? It's the same concept. If you already know the second derivative, you just take the derivative a third time to get the third derivative. Okay? So, our second derivative is 2 minus 2x to the negative 1, rewriting that. So the third derivative is going to be 0 minus 2 times a negative 1x to the negative 2. So that's a positive 2 x to the negative 2, which is 2 over x squared. Okay? Now, once you get past the third derivative, we don't keep putting slashes. It could get really messy. Alright? Once you get past the third derivative, we put the little parentheses and put a number in there. Okay? So this is the fourth derivative and the sixth derivative. Okay? Now, if I have the fourth derivative, what do I have to do in order to get to the sixth derivative?
Get the fifth derivative, get the sixth
Or just
derivative.
skip towards.
Yeah, okay. If I get the fifth derivative with respect to x would be what in this case? 2. So then what would the sixth derivative equal?
Non-existent.
Well, it exists, it equals 0. And actually, once I get to this point, the seventh derivative is 0, the eighth derivative is 0, the ninth derivative is 0.
Yeah, because it's gonna be 0, 1.
Yeah. Okay? So, that's everything that we wanted to cover here with the higher order derivatives and also our trig functions. Okay?